so it should be very difficult to be here at this time, at this third day and the last session. So I will be quick and gentle. So I will talk about our studies that we are currently working on last couple of years. And by the way, I'm Burak Toparli, and I'm the R&D manager of non-fasteners. And the thing is, we are working a couple of years about the effect of the socket depth of the fasteners, and this is one of the necessities which is driven by our suppliers. So we are working mainly on the automotive sectors, and if you consider the current expectation from the OEMs, from the automotive sector, is that we are trying to decrease the weight of our vehicles. If you look at from the internal combustion engine side, we know that there is the carbon dioxide emission, and we are aiming the carbon zero environment in the couple of years. So what automotive sector or OEMs are trying to do is to decrease their weight so that they can decrease their carbon dioxide footprint. And on the other side, if you look at the electrical vehicles or hybrid cars or the EVs or hydrogen powered cars vehicles, the main bottleneck is the range. So how can you increase the range? The easiest way to increase the range is to decrease the weight of the car or vehicle. So every OEM or every Tier 1 in working in the automotive industry in these days are trying to decrease the weight of their parts. So as a fastener producer here, we also working on how to decrease the weight of our parts or our fasteners. And so non-fasteners is located in Turkey, and it's the leading fastener producer in Turkey. So my company is my sponsor, so I have to help. And we are working quite different areas from mechanical material science, engineering side, and the industrial forestry side. And I'm also skipping this here. The thing is, we have different kinds of fasteners, and you may see in your daily life or on your automotive. So one of them are the internal socket type bolts. So when we look at the VDI 2230, which is a German standard, which is dictates us how to design bolted joints, this formulation is given in this handbook, and it is valid if your socket diameter, DM, is smaller than your shaft diameter. So, because of the necessity coming from weight reduction studies, we are also receiving this type of fasteners from our OEMs, our partners. So, the diameter of the socket is also larger than the shaft diameter. So, based on this formulation and from this VDI standard, we also work on how to correlate the maximum socket depth, which is dictated Y mean here. Then we work on how to create an analytical model of this. And in our paper published in the virtual conference on the European fracture, which is held last year, we presented this model. And we verified this with a finite element modeling, and what we did is, this formulation actually works like this. So, in normal bolts, you are expecting failures to be occur on the thread root. If there is any failure from the head region, this is indicating a material failure, production failure, or there is an issue in the assembly. So, what we are doing is we are comparing the stresses in the thread root and with the region here. So if the stresses are higher at the thread root, then my fracture or my failure will be on thread root, so I'm on the safe side. But if the stresses are here, the head region is higher, then I'm on the danger zone. So I must avoid. So the finite element modeling comparison and the validation is carried out in the previous study, and in this study that I'm going to talk about today is about the experimental validation. And we choose a matrix 8 bolts, and you can see here the diameter of the internal socket depth is higher than the shaft diameter. And what we did is we produced samples and we applied tensile tests. So we observe the fracture mode, which is either on the thread root or the under head region. And as you can see here, the example is where the internal socket depth is high, so that the failure is occurred on the head region. So this is a bad design, or not bad design. The socket depth is too large, too deep, so that the fracture is occurring under the head region. Then we conducted, we produced different bolts with different internal socket depth values, and we applied this fracture tensile testing so that the fracture is occurring under the head region or the thread region. So the thing is, this red dashed line dictates from the ISO standard. So ISO standard says that you cannot have fracture loss below this region. This is one hand. And on the other hand, we start our test and with different E values, and we observe a linear relation so that up to a point which is 2.73 here, my fracture load is now higher than the ISO standard. So in this case, I'm safe because I'm above the limit of the ISO standard. I'm also safe because my fracture is occurring on the thread root side. And this is another notation, so I can also give the V value, W value, so that I can correlate and still the same. So my fracture is always occurring on thread root region, and I'm above the fracture load that is dictated by the ISO standard. And this is the summary. So in the analytical model for this particular bolt, we found 2.82 Y mean, so the internal socket depth 2.89. And for the numerical model that we presented in the previous conference, it was 2.78, and with experiments, we achieved 2.37 of internal socket depth. So pretty close and pretty nice results. So at this point, we are what we have achieved is that now we have an analytical model which is estimating the critical socket depth for both sides, having the diameter larger than the shaft diameter, which is validated by finite element modeling and the experiments. So this is it. Thank you. I would like to acknowledge my company and the ICE for support. And thank you very much. If you have any question, please ask.
So, please. Thank you for your talk. I couldn't help but wonder, how does your analytical solution compare to just finding the shear stress and comparing it to the shear stress times the area of the circumference of the bolt?
This one? So the thing is, we are, the details you can find in the paper, and the thing is, we are comparing the stresses, and there is also a correlation, as you can see, from the torsional strength and tensile strength version. So they have the factor that is taken into account, and from this comparison, but based on this formulation, we calculate this Y mean value. I don't know whether I answer your questions.
Well, if you just take the area, say that it's the diameter of the bolt times the thickness underneath the head, between the head and the threads, and you multiply that by the shear stress in yield, then how does that compare to your analytical solution?
So I don't understand.
Maybe this is a question.
Yeah, you can do it.
Yeah, because this is just a test. Well, what's going to cause it? This failure is the shear stress. That's what
exactly.
And how if you apply a simple average shear stress calculation compared with the formulation you have proposed, how do they compare? Is that correct?
Yeah, that's what I mean. I mean, that we can make a very simple formula for that. And you have a very complicated formula, and I'm curious how the simple formula compares to the complicated formula.
Well, the thing is, it's because of coming from geometry. So where I took, So where this conic, the minimum distance between the internal socket and the radius, and how I can achieve this with this formulation.
Okay, thank you.
Thank you.
Thanks. Any other question, please? Go. So, thank you.
Thank you.